Please join me in welcoming Omri to the stage. Omri is a data hacker, a maker, and a Lego builder. Currently, he's the chief architect at Diagnostic Robotics, and he's building AI and predictive analytics models to help make healthcare better, cheaper, and more widely available. Welcome, Omri.
Hi, everyone. Good morning. Today, I want to talk with you about components, workflows, and cookbooks. But more specifically, what I want to talk with you today is about machine learning pipelines and heart attacks. But before I do that, I wish to do a short introduction. So I'm Omri. I'm an architect at a company called Diagnostic Robotics. I'm an engineer. While I'm not a data scientist myself, I can probably understand every second word that you say. And what we do at Diagnostic Robotics is AI-driven precision population health. And you might be asking what AI-driven precision population health means. It basically means something like this nice meme from the Liam Neeson movie Taken. One of the issues with healthcare in the United States and the world in general is that too many people don't get the healthcare that they need, whether it's because they don't have enough knowledge or whether it's resources or the fact that their insurance company can't give them enough attention. And what we're trying to do is basically look for the people that needs the most attention, that their condition might get worsened in the next few months or few years. And we try to find the best intervention for them, an intervention that actually can work and get them treated. Now, our story began like any other AI story with a notebook, a few data scientists that do some magic and get actually interesting results. And what we're trying to solve is actually find an intervention that we can do now to prevent hospitalization 6 months from now. And the results were very promising. And yeah, there was even a paper. But when we tried to get it into production, we got into the problems of getting to production, whether it's the problem of scale or the problem of governance or the problems of stability. And here enters MLOps. Now, MLOps is a lot of things, but today I wish to focus on pipelines. And pipeline orchestration is basically a solved problem. There are more than enough tools to choose from. And the tool we chose to use is Argo, and we love Argo, mostly because it's Kubernetes native and we are a Kubernetes workshop. It's API and CLI first. It has a really nice UI, and it allows us to create really robust deployments with Helm and ArgoCD, which we use extensively. And that allows us to take our AI, or basically very basic notebooks, and make them work at scale. And that's an example of part of the pipelines that we are doing, and that's actually a very small screenshot of a very long pipelines that runs above and below that screenshot. So excellent job, the business people said. Now, can you do the same thing for long COVID? And I've looked at data scientists in my team, and they looked back at me, and they thought for a second, said, okay, oh dear. Because while going from research to production, we've lost something in the journey. Because once we're looking on a pipeline, it might look simple enough on the demo, but reality is much more complex. And development of these pipelines become complicated, and nobody wants to work with 15,000 line YAML files to define these pipelines. And deployment becomes much more complicated because we have different models in different stages of life and different maturity that need to run together on the same environment and on the same data. And now you make sure that one researcher does not create issues or problems to other researchers or even our production code. And iterative experimentation became suddenly very slow. Once in the old notebook days, we just had to make a change, click enter, and see the change actually manifest. Now we need to wait for an image to build, we'll wait for a pipeline to actually be deployed, and then only run it. It can take a few minutes, and it really hinders our ability to run fast research. And that led us to understanding that when we're talking about an AI product or machine learning product, there are actually two modes we need to think about. One mode is the research mode, when we need to be very fast, very experimental, very adjustable, and it's more or less an iterative process. In this process, the data scientist is the king. And then there's the development and the production mode, when we need to think about scalability, reliability, making sure that this thing is governable. And it's especially important when we're talking about medical grade products. And we need it to work in a fire and forget mode. We cannot make sure that we always have a look and need to tend this pipeline and make sure that they work every day, every month. And in this stage, engineering is the king. But the issue is that with medical products, it's not just these two phases. It's actually a whole spectrum between them. So when we're talking about the progress or the spectrum between research and production, we're looking from the most basic steps when we're trying to do basic exploration and we are just going all over the place and looking for interesting data. And here we need to be very, very, very fast, and we don't care much for scale or quality of our code. And then once we go more and more towards production, we start to look into some things like retrospective studies, which actually need some governance and need some level of scale, but we still need the ability to react fast and to adjust fast. And once we move that, we need to pass clinical validation when an actual medical doctor looks on the model and actually signs it off. And then we need to make sure that our code and that our system is also governable and we don't just change things without any control. And when we go into prospective research, basically sending it into the market and having a test whether it works or not on real life, on real population, we actually need governance because we need to show results and we need to show that these results are valid. So MLOps, and the issue that MLOps adds complexity and it hinders our way to do experimentation. And the solution was surprisingly not more tools necessarily. The solution was architecture. So today I wish to share with you 5 lessons that we've learned about how to move from production to research, from research to production and back again. So the first lesson is to Pythonize your pipelines. And the reason why you might want to Pythonize your pipelines is, first of all, it's because it's developer friendly. People know how to write Python code. They don't necessarily know how to write YAML codes. They are much nicer to work with. And we can get all the nice things that we can get in code, whether it's abstractions or autocomplete schema validation, testing, linting. We can build our own opinionated API or scaffolds. And basically, once we have pipelines or treat pipelines as compilable code, it's much easier to bring engineering practices and patterns into the mix. There are several ways to do that. And the way we chose in the beginning was to just generate Pydantic code from the OpenAPI schema. But today there are a lot of nice tools, nice open source libraries you can use to generate pipelines from your Python code. And our first step was looking more or less like this. This is basically a low-wall pattern and how it looks in Python. But sadly, it was not good enough. It wasn't good enough because it wasn't easy enough for data scientists, and we've found more and more ways to make it easier for data scientists and data engineers to write better and better Python code. The issue that we find it complex is that for research, we actually some of the times needed to run these pipelines locally. We didn't want to do the entire process of pushing an image and pushing the pipeline to production and running it on a remote cluster for scale. Sometimes all we needed is to just run our code very quickly or just run our pipeline locally and maybe stop it or debug it in the middle. And when we try to do that, we've actually built another set of pipelines written in Python that can work only on our local computers. And now we suddenly have 2 sets of pipelines. One is a pipeline for scale, and one is a local pipeline for running locally and debugging. And this actually created an issue because we need to maintain both of these pipelines. And then we thought about it and asked, can we run our code locally for research and then run the same code without the need to maintain both code bases for scale and local research at Argo at scale? And we went back to the drawing board and thought about writing a little bit of a new DSL, a new library to write better pipelines. And here enters Pythonic DSL. What is Pythonic DSL? Well, Pythonic DSL is a mostly backward compatible subset of Python. What does mostly backward compatible subset of Python means? It doesn't mean that every code you write in Python will automatically get translated into Argo pipelines. It does mean that everything you write in this DSL can run locally as standard Python code. So let's have a look on how it works. So that's a very basic Python code, a very basic, probably the most basic MapReduce job that I can think about. And it looks like a legitimate Python code. It has some sort of a generate list that creates chunks of data. It has a very specific map task that should be parallelized and some sort of a reduce task that runs it all. In order to make it into an Argo DAG, all we need to do is add some decorators that defines which of these are tasks, which of these are DAGs that call other tasks, and the task where we wish to run them. This specifically, we want to run them on a Python 3 image. And the neat thing about that is, while basically we can create from the same Python method a workflow that will run at scale in Argo, this still works. We can actually still call the function MapReduce, and it will work locally. You can actually use this tool today. We've been using it in the last few months, and you can use it by going and pip installing Argo Workflow tools, and you can contribute to our GitHub page. So once we had this new way of writing pipelines, of writing workflows, it was time to start thinking about pipeline architecture. And when talking about pipeline architecture, I would like to talk with you about In-N-Out Burger. Now, if you don't know what In-N-Out Burger are, In-N-Out Burgers are a very famous fast food chain in the West Coast. And what they became famous for is the secret menu. The secret menu basically allows you to mix and match lots of the In-N-Out ingredients into some customizable meals with very crazy names like 4-on-4 Animal Style or the Flying Dutchman. But when you look a little bit deeper about the magic of the In-N-Out secret menu, the really neat thing about that is that they allow you to customize their menu to your will, but they are doing it with the same 4, 5, or 6 ingredients that they already have and they already use for their basic meals. And that's, I think, the really, really nice thing, because they allow you to customize your meal on one way, and on the other way, they do use use the same system, same ingredients, same processes that allows them to create something which is reproducible, that is always in a high level and very, very consistent. And I was promising to tell you about machine learning pipelines and architects, so that's probably the part about architects. So yeah, you can basically customize your burger into the crazy domains. Don't know why you would do that, but you can still do that. So what we can learn from In-N-Out on building our pipelines. So when we were looking on our pipelines, we actually split them into 3 types of pipelines, or 3 types of elements. One element is components. Components are basically reusable pieces of code and patterns that we wish to abstract away. Workflows are more or less like recipes. They are reusable atomic piece of work that can be consumed independently or as a part of a larger cookbook. And cookbooks are a combination of one or more workflows and cookbooks tailored for a very specific use, just like a very specific customizable menu that is tailored for a specific customer. So let's have a drill down and see how you use them. So the first thing is components. What are components? Components are basically pieces of the workflow that we wish to abstract from our users. Things like Kubernetes resource management, configuration injection, secrets, common environment settings, basically all the things that our engineers and our data scientists don't really care about. All they want is to configure their workflows and start running. They don't care about resource management for Kubernetes. And what we do with them is we actually try to take all this configuration and pack them as a really nice abstraction. In this example, this very specific configuration of a Kubernetes resource, we just named it as an ETL memory machine. And now when someone wants to write a pipeline that is intended for ETL, they will use this type of machine. And when they wish to use a pipeline or a task for training, they can use a training machine or a training with GPU machine and so on, without thinking about how it works behind the scenes. Another example for that might be how we configure a secret. So we just gave a nice name to all this secret configuration. And basically this piece of code is maintained by our DevOps team. In our engineering and data science teams don't need to know how secrets are handled behind the scenes. The next part or the next component is workflows. Workflow is an atomic piece of workflow, atomic piece of pipeline that can work independently, that actually as an input, as an output, it makes some sort of useful job. The basic difference between a workflow and just a simple DAG is that for a workflow, we define another decorator called workflow template. This basically tells our code to take this DAG, take off these dependencies, and pack it up and deploy it into our Argo cluster. Now we can use it and call it just from the UI. We can make sure that it's compiled and maintained in a very predictable, very maintained manner. The third part is cookbooks. So if we add components which basically talk about abstractions and workflow, which are reusable, well-maintained, production-grade blocks of work, now we have cookbooks, which are basically a mix and match of these well-maintained pieces of work, plus lots of ad hoc pieces of work or ad hoc workflows that we can mix and match together in order to create a customized workflow that we can use, whether it's for training or serving or whatever. So on the most basic manner, we can just use it to write down our entire pipeline or a customized pipeline for a specific use case. And if our use case just becomes more complex, we can easily change it. And if we wish to run it, let's say for testing, we can just add an ad hoc task called sampling and run it really, really quickly. And if we wish to just run an E2E test, we can take this cookbook and just wrap it with a few tasks before the cookbook itself that creates a test context and a few tasks when the cookbook ends that takes care for model validation or test cleanup. And this makes a lot easier. When we're talking about organizing these pipelines, there are a few ways we found that are effective. This is how we chose to organize it on diagnostic robotics. Basically, there are several folders split into components, workflows, and cookbooks, where workflows are basically the curated, shareable, reliable, and consistent building blocks, and cookbooks are mix and match of curated pipelines, environment-specific, task-specific, and even experimental pipelines. And the basic idea is that when you change something under the workflows folder, you need to make sure that you don't break anything. When you add something or change something under the cookbook folder, the assumption is that they don't need to survive long. So some cookbooks might need to survive more. There are more or less production cookbooks. Some are experimental and can live for 2, 3, 4 weeks until they're not necessary anymore. And this allows us to mix and match things that need to be more stable and things that need to be more experimental. The third lesson that we've learned is about deployment. So we've talked about how we have a cookbook menu, how we automatically deploy our cookbooks into our Argo clusters, so our data scientists can run their cookbooks from the UI. And that makes things a lot easier for them. But the issue with that is that very quickly we get a lot of junk into the classes. So someone wants to create a version with a small change. They don't want to hurt our developers. So what they do is they rename the workflow a little bit and push it. And then we get a lot of versions, small versions that we need to find if they need to be maintained or not need to be maintained. And the solution we find for that is just basically creating namespace isolation for pipelines. So basically, each branch in our Git receives their own namespace. When you push an update to Git, your namespace will be created or updated automatically, and it will never hurt other researchers' namespace. And each namespace can be isolated by resources and artifacts, so no data getting mixed between production namespaces and research namespaces. We basically use conventions to define these types of namespaces, naming conventions. There are namespaces used for serving. The branches need to be started with the word serving. There are namespaces needed for researchers, and there is a master E2E namespace intended for continuously validating the health of our system. We're, of course, using ArgoCD to deploy this. It makes our life a lot easier managing these namespaces. And one of the nice things is that in order to make sure that we don't get a lot of junk into our cluster, all namespaces are automatically pruned if are not used in more than 7 days. The fourth lesson I wish to talk about is about interactive experimentation. When we look on pipelines, especially in the experimentation phase, sometimes I would like to work on scale and then stop for a second, run a small code locally on my machine, have a look on it, maybe have a few iterations, and then once I'm happy with the result, continue with the entire pipeline. And the question is, how can I do that with Argo? And our experience in the beginning wasn't very nice. So it was a very fragmented experience. So we went into the code, started to write something up, started to run something up, and then went to get into the Argo UI, launch our own workflow from there, stop the workflow, get back to the ID, get back to the UI, and so forth and so forth. And some of the things that we found that became very effective in the small library that we wrote down is a library that allowed us to integrate our Argo workflows into our notebooks and into our basic debugging and research code. So basically, it looks like a very simple Argo client that allows you very easily to submit a job, whether it's a job that you've just created or a job that already sits on the cluster itself. And you can simply call a Python method and initiate this job, wait for it to complete and get all the relevant logs back to the console. You can suspend or resume a job, whether it's a long job, you can check for the status of the job if you wish. One of the nice things is that you will actually get the job results serialized and deserialized for you. So if you need to look into the outputs or artifacts of the jobs, all you need to do is just call results that outputs, name the output, and you can treat it just like a regular Python object, Python dictionary. And the same goes with artifacts. If you wish to read the CSV results, you can easily do that. And the really nice thing is that it integrates well with our Pythonic DSL. So we can take this code back with, we can take the code that we wrote, we can take the pipelines that we wrote in a very Pythonic way, and on one hand, run it locally, and on the other hand, with 2 lines of code, run it on a cluster, which make things a lot easier. So these are the 4 or even 5 lessons that we need to learn from this. So one thing that we've learned is, and that's probably the basic lesson behind it all, is to understand that there is a duality between research and development processes. The second lesson is how to treat our pipeline as code. And it's not means to write our pipeline as code, but actually treat it the same as code. So make sure that we can run it the same way that as we write and run our code. The second lesson is pipeline architecture, is to think about how to build your pipeline to be reusable and be stable over time without losing the ability to do research. The third lesson is about deployment. And the fourth and last lesson is about how you can integrate interactive experiments with code that need to work on scale on a cluster. So that's basically it. I invite you to go and use Argo Workflow tools and the Pythonic DSL that we wrote and the client API that we wrote. If you wish to talk more about how to create better Argo pipeline and Argo pipeline architecture, you can find me at my email or at LinkedIn. So thank you very much and have a great day.